lesson on graphs of exponential functions. Again, we're going to start with a warm-up, just so please have your graphing calculators ready so you can practice doing some of these normal distribution problems from before. So the first question is, the student of class X sat a physics test. The average score was 46, so we can write the mean, mu, 46. Okay, what's going on there? Let's fix that. One. Okay, good. So mu 46, the average score is 46 with a standard deviation of 25. So our sigma, therefore, is 25. Good to write those out again. The teacher decided to award an A to the top 7% of the students, so the top 7%. Assuming that the scores were normally distributed, so that gives you a clue in the exam that it's a normal distribution problem. Find the lowest score that would achieve an A. So the good thing is, in these kinds of questions in the exams, they normally have the word normally distributed in there somewhere to give you a clue. So for the top 7% of the students in this class score an A, we want to know what the lowest score is. What's the lower boundary for that? So let's try drawing the diagram. You would do your normal distribution, your bell curve, and you would draw in your x-axis. Maybe I should change back to the other one. Then you would do your x-axis. And notice if it's the, and mark in your mean as well. So if the top, 7%, what's 7% as a decimal? Divide by 100 and you would get 0.07. So the top 7% get an A. So the students in this area, they receive an A in this test, physics test. They want to know what's the lowest score that would achieve an A. So we want the lower boundary. But remember, so if we want a boundary, do we do the normal CDF on the calculator or do we do the inverse norm? Just think of that. And what I mean by that, if you're not sure, is, like, remember you go second vase. Which one do you choose? You never choose the first one. Do you choose the second one, normal CDF, or the third one, inverse norm? If we're trying to find a boundary and we're given the area, the probability. So I think, yep, you're right, we need to do the inverse norm. But remember what goes into the calculator, it's not the area to the right of the boundary, K, it's the area to the left of the boundary, K. So remember the whole area, by definition, is under the curve, is equal to 1. So to calculate, if this area here is 0.07, the area to the left must be 1 minus 0.7. So area to the left is 1 minus 0.07, sorry if I said 0.7, 1 minus 0.07. Plug that into the calculator, what area do we get? We get 0.93. So the area to the left of the boundary is 0.93, and that's what has to go into our calculator. So let's practice doing that again. Grab your calculators out, I'll just go back to the beginning. So to do a normal distribution problem, we would go, we need to open distribution, so to remember to do that we go second vase, and we don't want to calculate the area, we already know it, we want to find the boundary. So do this inverse norm, you're doing the reverse step. Inverse norm, the area that has to go in is the area to the left, so we put in 0.93, enter, and then we plug in our mean, our mu, which is 46 for this one, and our standard deviation, sigma, which is 25. And we go down to paste, press enter again, and we've got the pass mark. The pass mark is 82.9. So it's saying that the lowest mark to get an A is 82.9. So that's our answer, 82.9, rounded to 3 sig figs. Again, strongly suggest in the exam, write out the unrounded answer and then round to 3 sig figs. So if you make a mistake rounding to 3 sig figs, you might not be penalised for it. So that's that one. Let's go on to the next one, question 2. We've got the lengths of screws produced by a machine are normally distributed. So as we said, they always tend to tell you this, that it's a normal distribution with a mean of 75 millimeters. So we can write mu, 75, and a standard deviation of 0.1 millimeters. Always check that are they in the same units, and yes they are, they're both in millimeters. So we can put them together. If not, you'd have to convert one of them so that they're the same units. If a screw is too long, it is automatically rejected. If 1% of the screws are rejected, try to think 1%, what area would that be? Divide by 100. 1 divided by 100 is 0.01. So if 1% of the screws are rejected, what is the length of the smallest screw to be rejected? Again, it's a really good idea to try drawing this information. So not many are rejected, because only like 1%. If 1% are rejected, that's a tiny amount. So a tiny amount down the bottom are rejected, and that's because they're actually too long. So find the length, but we want to know what's the length of the smallest screw to be rejected. So all of these would be accepted, but some of them are too long, and we want to know what's the smallest length for the one that would be rejected, I think. Okay, anyway, let's keep going. So to plug this into the calculator, we would just go, just thinking, have I done this right? I hope so. Second vase. So we want to find, we know the area is 1%. We want to find what the upper boundary is. So it's an inverse norm. Normal CDF is when you want to find the area, or it says find the area or probability, but we want to find the boundary. So we've got to enter in, all right, the area is 0.01, 0.01, enter. The mean is 75. Standard deviation is 0.1 according to this question. So they're saying that the smallest screw to be rejected is 74.76. And so on. So write that out to as many digits as possible, and then round to 3 sig figs. And put units in there too. So to 3 sig figs, that rounded to, as you can see, 74.76. The 6 rounds are 7 to an 8, so 74.8. Okay, if I did that right. Okay, moving right along. The weights of cabbages sold at a market are normally distributed with a mean of 1.6. So let's write mu. This funny u is 1.6, and a standard deviation of 0.3 kilograms. So that is 0.3, our sigma. One wholesaler buys the heaviest 10% of cabbages. What is the minimum weight cabbage he buys? To do a sketch, it's always good to do a sketch because sometimes that counts as a method mark. So really make yourself, in the tests and the topic assignment and the exams, make yourself do a little sketch. There you go. Radio. So what it's saying, the heaviest 10% of cabbages is here. So the lightest 90% is here. The heaviest 10% would be here. What's 10% as 10% as an area? Let's see, what would it be? 10% as an area would be 10 divided by 100, which would be 0.1. So it's a tiny area. We want to know what's the minimum weight of cabbage that he buys, because he only buys these the heaviest 10%. What's the smallest boundary? So what's the lower boundary? So try to think, remember what goes into the inverse norm on the calculator. It's not the area to the right though, it's the area to the left. So we can easily work that out because we just go area to the left. As we said by definition, the area under the whole thing is 1, so the area to the left must just be 1 minus this area. I'll give you that unshaded area. So 1 minus 0.1 would give you 0.9. So 0.9 is the area to the left of the boundary that we want to find, so that's what has to go in the calculator. Let's plug that in. Clear. Go second vase. We want inverse norm, so third one. The area that goes in is 0.9 we should be putting in, so 0.9. Mean is 1.6, and standard deviation is 0.3. Okay, so what's that rounded to 3 sig figs? Write it unrounded, and then round to 3 sig figs, so 1.98, because next to the 8 is a 4. So 1.98, make sure to note any units. It's kilograms. We're talking about weights of cabbages. And again, another person chooses cabbages with weights in the lower quartile. Trying to think back to statistics, lower quartiles, upper quartiles, interquartile ranges, that kind of thing. What is the heaviest cabbage this person buys? So just to remind you of what we mean by this, so I'm just going to show you a box and whisker plot. I'm going to have this ready for you, sorry. Box and whisker plot, let's look up an image of one of those. This is a good one. Let's view this image. So box and whisker plot, just reminding you, what is the lower quartile? So remember, you've got, in a box and whisker plot, you've got the minimum, lower quartile, median, upper quartile, and maximum. So the lower quartile, from below the lower quartile, that splits it into 4 quarters. So 25% or a quarter, so 25% must belong here, 25% of the people must belong in this group, 25% of, the cabbages must belong in this group, and 25% belong in that group. So below the lower quartile is 25% because it breaks it into 4 quarters. That's why they're called quartiles. So let's see, another bug chose cabbages with weights in the lower quartile. So in the lower quartile, meaning the lowest 25% is what we mean by that. So that helps us to realize what the area is then. What is the heaviest cabbage the person buys? So let's just write this out. The lower quartile contains the bottom 25% of the weights. So the area to the left of K must be 0.25. That's what we're saying here. So the lower quartile contains the bottom 25% of the weights, as we said according to this, bottom 25%. So the area to the left of K must be 0.25, 25% divided by 100. Again, let's draw a diagram so we can get a nice little method mark for this maybe. Drawing a normal distribution, and that's 0.25. We want to find what this boundary K is. So we're practicing inverse norm stuff for this whole warm-up. So what do we need to put in? We still have the same mean and the same standard deviation. We've just got to put in the new area. So let's clear that. Let's go second vase. Inverse norm because we want to find a boundary, not a probability. So the area to the left is 0.25, all below the lower quartile. And same mean and same standard deviation, which makes it easy. What would that be to 3 sig figs? Write it unrounded first and then round to 3 sig figs. 1.39, but next to the 9 is a 7. So that's going to round it up to 1.40. Try to think what are the units. It's weights of cabbages. Have a look at what they've got. They've got kilograms. There you go, warm up done. So you'll still need your graphing calculator because you're going to be doing a fair bit of graphing for this part. The general equation of an exponential function. Remember exponential functions are kind of these ones that kind of go up like that. Like exponential growth, like radioactive decay, exponential growth of population, that kind of thing of animals or humans. They can also have exponential growth and you can have exponential decay. They're special kinds of graphs that you tend to find kind of in nature and society to some extent. So that's why this kind of mathematics has been invented. So the general equation of an exponential function is y equals Ka, these are just numbers, to the power of x. So notice that the x is up here, y is here still, x is up here, plus c. So looking at this general form of the equation, why do you think they're called exponential functions? Like, why do you think the word exponent is in there? Have a look, and you might realize it's because of this. What is x in this case? You're right, the x is an exponent. So the variable x is an exponent. That's why they're called exponential equations. Because you've seen other equations like quadratics and linear graphs, but the x is not an exponent in those. In these particular graphs, the x is an exponent in their function. Why was this mathematics invented? We'll just go over this quickly. So like with the normal distribution, as I said, there happens to be a lot of phenomena in nature and society which follows this exponential growth, like starting off slowly in growth and going up rapidly, or exponential decay, like dropping rapidly and then dropping slowly. For example, the spread of viruses like Ebola or Zika, one person infects multiple people, actually more so like swine flu, that kind of thing, more rather than Zika. So the spread of viruses like Ebola, one person infects multiple people, particularly like if it's a sneezing kind of virus. Population growth, e.g., each person gives birth to multiple offspring, so that's why population grows slowly, but as multiple offspring then give birth to more multiple offspring, grows rapidly. So that's taking it things like plagues, like mice plagues and things like that. So bacterial growth in a petri dish, it grows slowly to begin with and then starts growing rapidly after time. Radioactive decay decays rapidly and then really slowly towards the end. Growth of weeds in a field, they grow really slowly and then suddenly bang, they grow really rapidly. The decay of drugs in your bloodstream, that's an interesting one. So if you are injected with penicillin, so you've got a lot of penicillin in your blood initially, it decays rapidly. and then it slowly peters off. So you still have small trace amounts of drug in your blood. And same with insulin, for example. So that's why this mathematics was invented, because it's found to have some relevance in the real world. You may be required to complete a table of values for the exponential equation and plot the graph. So let's just do an example of where you're just asked to fill in a table of values using an equation and just plot the points and draw a curve. So let's say the population of fleas on a dog after T days is modeled by n for the number of fleas equals 4 times 2 to the power of t over 4. So see, it does kind of look like a exponential equation still. It's kind of got an exponent and it's got a constant. So long as you've got something to the power of a variable, like something to the power of x. But in this case, we've got t instead of x. It's an exponential equation. So if you see an equation where you've got something times something to the power of a letter, normally think exponential equations, exponential functions. So some values are filled in on the table, but they want you to fill in the missing ones. So the missing ones are p here and q here. So all you have to do is substitute in t into the equation. And here, see this t is greater than 0? It's just pointing out that, like, you know, for this equation, t is greater than 0. So because we don't have negative days, so it's possible we would only have positive days. It makes sense in terms of the real life situation. We're not going backwards in time, so that's why t is greater than 0. So write down the value of p. We need to show working out steps, so make sure, if t is 0, make sure you write 4 times 2 to the power of 0 over 4. Make sure you do that, and you can get a method mark for that, and then you can plug it straight into the equation, just like this. Just because you've got that nice fraction button. Remember, you go alpha y equals to make that fraction. I'll do a little demo of it for you if you like. Clear. Always good to see a little demo on the calculator. 4 times 2 to the power of, remember you do this to do the exponent, and remember you go out to make a fraction, to make 0 over 4, you go alpha y equals n slash d, numerator, denominator. See, it's made a nice fraction. 4 times 2 to the power of 0 over 4. Lovely, enter. What answer do we get? We get 4. Makes sense, at times 0, we'll have 4 fleas, but let's see what happens. Notice that this shows some kind of growth. So by the time is at 16 days, we imagine there'll be a lot more fleas on this poor dog. So 4 times 2 to the power of 16 over 2. So make yourself write this out. The 2 doesn't have to be in brackets, but I just do because that's what they did here. 4 times 2 to the power of 16 over 4. Plug that into your calculator instead. 4 times 2 to the power of, go alpha y equals n slash d, 16 over 4. And you get 64. So after 16 days, this poor dog has 64 fleas on its body. Now you just asked to plot them. So at 0, we're going to plot 4. At x equals time is 4, we're going to plot 8, and so on. So you'll notice that when you do that, so let's see, what have I got here? So you might want to label your axes, of course. So we need to, our x values need to go from 0 up to 20, and our y values have to go from about 0 up to 130, for example. So in the exam, they always tell you exactly what scale to use, but this is not an exam, so I'm going up by 2s, and I need to go up to 20. And I should definitely label it T for time. And I need to go up to 130 here, so I'm going to choose to go up by 10s. So if I do that, I can fit it all in. Up to 130. And what should I label this again? It's N. Now the first point was 0, 4. So plot your 0, 4 point. I tend to just plot all the points. Next point you can see is 4, 8. So 4 matches up with 8. Next one is 8, 16. Go across to 8, go up to 16. Which one here is pretty rough. About there. 12, 32. 12, 32. Again, just pause if you need to look at these for a bit longer. 16, remember, it equals 64 according to our calculations. 16 and 64. Oops, ignore that pink line for now. That's part of something else. So I'll just do that. 64, there it is. And 20, 128. So 20, we need to go up to 128. So let's plot our point. And exponential graphs That's a point there, you can't see it really well. Exponential graphs are kind of like these curves, so we shouldn't draw lines through them, we should draw a smooth curve. So let's draw a smooth curve through those points. Ignore the pink for now, that's part of another question. So there's your exponential graph plotted. And what's the next question? We've done that. Oh, they did actually give us instructions. Use the values in the table above. Draw a graph from 0 to 20. So they told us go from 0 to 20. Use one box to represent 2 days. So that's what I did. I went across 2, 4, 6 on the horizontal axis and one box to represent 10. So they did tell us in the question, but luckily I did that. So make sure to follow whatever they tell you to do in the exam. So use your graph to estimate the number of days for the population of fleas to reach 55. So population of fleas is here, number of days is here. So population of fleas being 55, it's just right in between 50 and 60, isn't it? Right there. So do a dot, 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 make sure to show your dot, 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 hit the graph and then read down. Well, how many days is that? What would you say? Roughly 15 days. So that's an example of just some basic graphing ones, which you might have been okay with, but it's always good to do a little practice of that, just in case you're not. Now into examining some trends. So I've actually done some graphs for you, but I'll show you how I kind of got them. So here's a general form of an exponential function, y equals ka to the power of x. X is the exponent, of course, plus c. C could be 0, k could be 1, that's fine, a is normally a number. So look at the graphs and describe the effect of changing the variable. So you probably can't see it on here, but on your ones, hopefully you can see it. We've got different graphs here. And then we've got y equals 10 to the x. What was this one? I'm not sure what that one was, but on your original copy you can probably see it. It's got a different value of a, so basically a is a different number. And this one on my copy, I can't really see it either. So a different value of a, but on yours you'll see it. If you plug them into the graph, I'll show you how to graph. If you forget, maybe go y equals. So y equals, let's do 10 to the power of x. Remember x is here. 10 to the power of x, and then graph. You might need to adjust your axes. So that's a general form of it. Maybe adjust your window so that it matches these ones. -4. I seem to go up to -4 up to 8. So my window, I'm going to make my x-min go from -4, because my horizontal axis seems to go from -4 to 8. And leave that one. Y-axis seems to go from about -1 up to 8. -1 up to 8, so I'm just going to match the axes that you were given. And now let's graph and see it kind of looks a bit more like this now. So there you go, so that's how I graphed 10 to the power of x. Notice it cuts through 1, so its y-intercept is at 1. If you also plug in these ones, I'm not sure what this one was, maybe it was something like 8 to the power of x, 8 to the power of x, graph what that one looks like. See, it just graphs another one for you. No, obviously it wasn't that one. I'll just pause and I'll open. Okay, I'm back now, and I've opened the original document. Yeah, so it's 10 to the x, 3 to the x, 2 to the x. So we've graphed 10 to the x, so instead of 8 to the x, I should have had this one, 3 to the x. 3 to the power of x. Okay, let's clear all that. It's a bit messed up. 3 to the power of x. Graph. So here's the first one coming through, 10 to the x. I've got different colors, of course, on here. Here comes 3 to the x. Slowly coming through. Notice it still is cutting through 1. And then y equals, let's do this last one, 2 to the x. So this is a little demo of how you would graph these. I'm not going to graph all of them because they've been done, but it's good that you practice graphing and adjusting your window. That's it. So there's 2 to the x. What do you notice about them all? Right, so I need to go back to here. So what is the effect? So they all seem to have the same y-intercept, but their y-intercept is all 1. So we can say y-intercept stays the same. As the value of a changes, say it gets lower, what happens to the graph? So as a increases, the graph moves upward more rapidly after the y-intercept. They seem to be quite similar here. But if you've got a higher value of a, like a is 10 compared with 2, it increases more rapidly after the y-intercept. So as a increases, the graph curves upwards more rapidly after the y-intercept is what I've written there. Next one, so that was changing a. What happens if we experiment with changing values of k? So different values of k, notice my a is always 2 for all of these. I'll go back to the original one so you can see it a bit better. Notice a is 2 for all of these, but I'm sometimes putting k here. K is 1 for this one, k is 0.5 for this one, k is 3 for that one. Again, you would just graph it in the calculator. I'll do one really quickly for you. Let's clear them, clear, clear. 3.2 to the x, that means 3 times, because it's 3 times, you can do brackets instead if you want, 3 times 2, you've got to have some kind of multiplication, to the power of x. Then you would graph it, same axis as before. Here comes the graph, very slowly. Oh, it's graphed here for you anyway. So what do you notice? The y-intercept was always 1 here, but if you put k as 3, it's going to multiply the y-intercept by 3. So the y-intercept suddenly is going to be 3. If your k is just 1, because that's 1 times 2 to the x, I don't know what went wrong there. Oh, anyway. So 1 times 2 to the x, y-intercept is still just 1. 0.5 times 2 to the x, the y-intercept is suddenly 0.5. So this seems to really affect the y-intercept. So you can say, basically, k is the value of the, try to think, y-intercept. So the k value is telling you what the y-intercept is going to be, because k is 3, y-intercept is 3, k is 1, 1, 0.5, 0.5. Next one along, making k negative. You can't see the k there, but on yours it says k negative. So k is this one. What happens if you make this number a negative? So I've put one where k is positive. This is an example of one where k is positive. These are examples of when k is negative. So basically it just makes the graph curve downwards instead. So if k is negative, just flips it so it goes downwards, reflects it across the x-axis. What's the effect of changing c? Let's see, what is c? C is the constant term at the end. So if you change c, basically, let's have a look up on here, on the original one. If you change c, I just have to scroll down a bit. Okay, changing c. So we've got here c, they're all 2 to the power of x, but here I've got +1, I've got +0 here, and -2 here. So just basically it's the same graph. Notice it's exactly the same graph. It's just been moved upwards. It's not like the gradient or anything of it has changed. It's just been shifted upwards. So the blue graph is exactly the same as the pink graph. It's just been shifted up. And the blue graph is exactly the same as the green graph. It's just been shifted upwards. Everything's gone up a step. So what can we say about that? We can say that the effect of changing c shifts the graph upwards, or if it's c is negative, downwards, if it's lower, but doesn't change the overall shape. So changing c doesn't change the overall shape, it just makes the graph either shift upwards if it's positive or downwards if it's negative. And the last one's making x negative. What is x? Remember, x is the exponent. So if you make x a negative number, for example, 2 to the power of negative x, 5 to the power of negative x, they kind of represent decay. This is what we call decay, where it starts up high and drops, like medicine in your blood. You have a high amount and then it slowly decays according to these equations, or it decays rapidly and then slowly, rapidly then slowly. If x is positive, it's just these normal growth graphs, like populations grow slowly and then rapidly, slowly then rapidly. So what's the effect we can write? So it makes the graph reflect, kind of like mirror image across the y-axis. Makes the graph reflect across the y-axis. If x is negative, it looks like an exponential decay graph, like a decrease graph, as opposed to a growth graph. So making x negative makes it look like a decay instead. What's the effect of making a between 0 and 1? So in all of these ones, a was like 2. A was 2, see? So a is that number. What if it's a number that's between 0 and 1, like 0.2 or 0.35? So for example, if it's 0.3 to the power of x, that also turns it into decay. So if a is between 0 and 1, it's a decay. But if you have it between 0 and 1 and to a negative, it kind of counteracts itself and makes it back into a growth. So it makes the graph making exponential decay instead of growth. Basically talking about that one. But if you do both of these things, then it kind of just makes it a regular growth one as well. So that was a whole heap of graphing. So basically what was the point of that was an investigation to find out what are the effects of changing the values of these things. So I'm not sure, is it missing? The K is kind of missing on your one, so I'll just draw it in. I don't know why it's missing on yours. It's on mine. It's okay. So yours might have it there already. So how would you describe the overall effects of on the exponential graphs of on the previous page when you change K, A, X, and C? So they all have the following domain. So domains, let's have a look. What do I mean by domain? Remember, it's where does it live on the x-axis. So would you agree they continue infinitely in this direction and infinitely in that direction, but they never cross the x-axis. So generally, it's supposed to be it goes on infinitely in either direction. So the domain, remember, it's infinite horizontally, XER, meaning all real numbers are possible, because it goes on infinitely that way and infinitely that way. They all have a something asymptote. They all have a horizontal asymptote with the equation y equals c. What do I mean by that? Horizontal asymptotes. Asymptotes are parts of the graph where it's not allowed to live. So on your graphs, you might want to draw in these asymptotes. So these graphs, they kind of continue on infinitely this way. They never cross the x-axis. So you put in a dot, dot, dot on your x-axis. And that's your your asymptote, y equals 0, horizontal asymptote. These ones also have a dot, dot, dot. You can't really see that well on my copy. Dot, 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 pink line. And with an equation, y equals 0 for that one too. These ones also have horizontal asymptotes, y equals 0, because the graph goes infinitely this way but never crosses the x-axis. These graphs also go infinitely this way but never cross the x-axis. That's just a special thing about these graphs. Whereas these ones, because you've got a value of c has shifted everything up. So for this one, 2x plus 1, the asymptote that used to be at 0 has now moved up to y equals 1. And for this one, 2x minus 2, the asymptote that used to be at 0 has now shifted down to y equals negative 2 for this one, and y equals 0 because that's just a regular one. These ones also have horizontal asymptotes at y equals 0 and y equals 0. So they all have these horizontal asymptotes with equations y equals c. So if you were told the equation is y equals 4 times 2 to the power of x plus 7, then the horizontal asymptote is y equals 7. The x variable is always an, you probably realize it's an exponent. The higher the value of a or k, the more rapidly the graph curves upwards or downwards. That was an example of the first one. See 10 compared with 2, it curves more rapidly upwards. If a or k are negative, the graph curves downwards. Changing the value of c makes the whole graph just shift upwards or downwards. It doesn't change the general shape. The ranges of the graph are determined by the asymptote, because you can see the asymptote is kind of like the lower boundary of these ones. So the range for these ones would be y is greater than 0, not including 0, because the asymptote means an area where the graph doesn't exist. For these ones, the range would be y is less than 0. For this one, it would be y is greater than 0. For this one, the asymptote is at y equals 1, so the range would be y is greater than 1. For this one, the asymptote's at y equals negative 2, so the range would be y is greater than negative 2. Kind of getting through this slowly. If a is greater than 1, then we see exponential growth. So if you've got like 2 to the power of x, you get growth. If a is between 0 or 1, like a little decimal fraction thing, x is made to be negative, we see exponential decay. So this would be an example of like 0.5 to the power of x, because it's between 0 and 1. Next, let's keep going. So now you're asked to just do some freehand sketches of the following based on your observations from those previous 2 pages. Make sure to always draw in the horizontal asymptote using a dashed line, and to write the equation of the asymptote next to it. You should always label y, the y-intercept also, and you can calculate it by just substituting in x equals 0 into the equation. So let's do that. So here's your function, fx equals 2 to the x plus 1. What is our horizontal asymptote going to be? So our c value is 1, so we're going to have a horizontal asymptote at y equals 1. So we can do, that's meant to be a dot 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 line, so that's our dot 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 line with the equation next to it. Now the actual function, 2 to the x is just a regular one, so it's going upwards. Normally the y-intercept for this would be at 1, but because everything's been shifted up by 1, that's why the y-intercept is at 2 now. If you weren't sure, just plug in 2 to, because at the y-intercept, cx is 0. Plug into the calculator, 2 to the power of 0 plus 1, you get 2. And it's a general growth, because that is a value greater than 1. It's not between 0 and 1. It's not like 0.5 to the x, and x is positive, so up to growth. Now do freehand sketches of the following. So I've kind of done them roughly, if you can see them. So do your x and y axis. Y equals 3 to the x, so we'd have a horizontal asymptote at y equals 0. And 3 to the x is just a regular one, so it'll have a y-intercept of 1, and it's a growth. Whereas 3 to the x plus 1 would have a horizontal asymptote at y equals 1, because everything's shifted up. Its y-intercept would now be at 2, because if you plug in 0, you'll get 2 as being your answer, and it's still just a growth. So it's the same graph, it's just been shifted up. And make sure to label it and everything. So y equals 3 to the x, same thing, horizontal asymptote at y equals 0, y-intercept of 1, here's your graph, y equals 3 to the x, and y equals 3 to the negative x, that's the one where you just reflect it, it's a mirror image. So 3 to the negative x is just going down like this way instead, it's just reflected across the y-axis. Next one, y equals 3 to the x, regular one, horizontal asymptote at y equals 0, and y equals negative 3 to the x. Oh, sorry, here's y equals 3 to the x here, y-intercept of 1. Y equals negative 3 to the x. If you plug in negative 3 to the 0, you get negative 1 as your y-intercept. And so see, it's just been reflected across the x-axis. So it's the same graph, just reflected across the x-axis, so you can label it. Y equals 2 to the x, we'll have a horizontal asymptote at y equals 0. So this one also, by the way, has the same asymptote, y equals 0. And so same with this one has the same asymptote as the other one. So y equals 2 to the x, if you plug in 0, you get y-intercept of 1, do a rough sketch of it. And y equals 5 to the x, remember the more high the value of a, the more rapidly it curves up after the y-intercept. So y equals 2 to the x is this kind of one that curves up lower. Y equals 5 to the x, it goes to about the same point here and then curves up more rapidly afterwards. That's all based on observations from before. Let's do this page. So here's your GDC. Sorry, just 1 second. Right here we've got exponential growth and decay word problems. So growth. Growth meaning like goes up like this, decay means it goes down like that. So we're just applying it now. So a population of 100 mice is increasing by 20% each week. To increase the quantity by 20%, we multiply it by 120% or 1.2. So if population with respect to n is a population after n weeks, then p to the 0 is 100, the original population, because it starts with 100 mice, so the first point would be 100. P to the 1, you would have to plug that in. P to the 0 times 1.2, 100 would give you 1.2, will give you that answer, and so on. From this pattern anyway, we see that the function, basically this is what you need, the function that we want is 100 times 1.2 to the power of n. So that's your k value, that's the initial population, 1.2 is like your a value. And that was calculated because it was a 20% increase. So remember, like back to decimal multiplier from middle school, 100 plus 20 over 100 gives you 1.2. So where does 100 come from? It's the initial population of mice. Initial population of the mice at t equals 0. Where does the 1.2 come from? As the population is increasing by 20%, we say the rate is 100 plus 20 over 100. If it was a decrease, it'd be 100 minus 20 over 100, so which is 1.2. Another example, an entomologist monitoring a grasshopper plague notices that the area affected by the grasshoppers is given by the area, like of grass, is 1,000. times 1.15 to the power of n hectares, where n is the number of weeks after the initial observation. So what is the size of the original affected area? Remember, it's this amount here. You could always just plug in n is 0, like times 0, 0 weeks, and calculate it. You'll get 1,000. But you can also just look quickly there. It's 1,000. It's not 1.15, it's 1,000. 1.15 is the rate. Find the affected area after 5 weeks. Okay, so after 5 weeks, you just plug in 5 into here. So you go into the calculator, you go 1,000 times 1.5 to the power of 5, and you get this answer here, which is about, rounded to 3 sig figs, 2,010 hectares. After 12 weeks, same thing, plug it into your equation, just put in 12 instead, and you'll get this answer, which the 3 sig figs is 5,350 hectares. Write the unrounded answer first, though. C, draw the graph of a to the n against this. So you can just plot these points. You can plot the initial one, plot it at time 5 weeks, you get that. At 12 weeks, you get that. So let's do a quick one. So notice it went up to about 6,000. So we've got our x-axis, which you can't really see, but it's going up. My x-axis looks like it's going up by 2s. 2, 4, 6, 8, 10, 12 you should have here. And it should have n for the number of weeks. And a to the n should be up here, but you can't see it. You can sort of see it a bit there. And then if you plot at 0 and 1,000, plot at 5, is that about here? 5 and 2010. Show you the 3 points. 5 and about 2010, and 12 weeks and about 5,350. And then you just draw a smooth curve between all of that. How long will it take for the area affected to reach 10,000 hectares? So they've told us instead what the area is. They want us to work out the n. So let's get a method mark by just plugging that in. 1,000 times 1.15 to the power of n set equal to 10,000. They want us to find out what the n is, which in math studies we're not required to do that with algebra. You'll get a method mark for doing this. They expect you to do it with a calculator. So what they expect you to do is they expect you to graph. So go to y equals, plug in your function, 1,000 times 1.15 to the power of x we use. So power of x. And then also plug in this graph, y equals 10,000. 1, 2, 3, 4, y equals 10,000. And graph it. And you probably can't see anything. And that's because the y needs to go, your window is kind of set so that it's kind of like this. But your y value has to be higher than 10,000. It has to be higher than that.